All right, so maybe let's start. Welcome to this session on ODEs and PDEs, and thanks for sticking around. We have a list of 5 fantastic speakers. I'm really looking forward to them. I'm co-chairing this session with Nick Boffi, who is online here as well, and he will help me chairing the session, and we will monitor the chat and also the Slack channel, so please use all those channels to post questions, make comments. We start with the spotlight presentations, and then we have time for discussion. So maybe Stefan, you can start sharing your slides and take it away. Each of the speakers has 5 minutes, and please stay on time so that we have time for discussion.
All right, thank you for the lovely introduction. I wanted to talk to you about some observations on high-dimensional partial differential equations, and specifically PDEs with data which are represented by, in this case, infinitely wide neural networks with one hidden layer. So the goal of our research was to develop a regularity theory in function spaces which are specifically adapted to neural networks that sort of mimics the classical developments, and particularly in function spaces which are well suited, in which we can know that we can deal with the curse of dimensionality, because we know that for certain classes of PDEs, we can find solutions effectively using neural networks, but we were looking for a principled function space approach. And the starting point is if we just look at the heat equation, and the initial datum can be represented as this kind of expectation. So this would be an infinitely wide neural network where instead of a sum of AI activation of WI times X plus bias, we just have an expectation as an infinite kind of sum. Then we can use the exact representation formula by convolution with a heat kernel. Because everything's linear, we pull the expectation out, and we see that this function is in a specific space for these kind of infinitely wide networks, which is a Barron space. And it's a Barron function in X and square root t because of parabolic scaling. And it is a Barron function in X only, but the Barron norm may grow with time. So here so this is very much linear and everything is explicit. We can also consider some nonlinear PDEs, like this viscous Hamilton-Jacobi equation, where we've got a source term on the right-hand side, which is related to the slope. And the nice thing about this particular Hamilton-Jacobi equation is that we can write down an explicit solution, namely, if we solve the heat equation with slightly different initial data, and then we take the logarithm of the solution, then this logarithm precisely solves our original Hamilton-Jacobi equation. So on bounded intervals, the exponential function and the logarithm can be represented effectively using shallow neural networks. And if we have a composition of linear map, nonlinear, linear, nonlinear, etc., and we just combine where two linear maps meet to one single linear map, then we get, again, a neural network. So we can do the same thing with infinitely wide neural networks. And this way we can write the solution to this nonlinear PDE as a concatenation of Barron functions. And for this, we can obtain estimates in a function space which corresponds to deeper neural networks. So these are two positive examples. On the other hand, if we are looking at a bounded domain like the unit ball, and we're solving we're looking for a harmonic function with boundary values which are a single radio activation. So we note then the question is this function in a Barron space? And if it is in a Barron space, then we can define it on the whole space by, not uniquely necessarily, but because we've got this explicit representation formula. Now we note that the equator in the sphere is part of the set where U is not differentiable because ray U is not differentiable. And the central plane inside this, inside the ball is not part of the set where we are non-differentiable because harmonic functions are smooth. And then there is a structure theorem for the singular set of functions of this form, which says that vaguely the singular set of a barren function is straight, or a union of straight pieces. And this is a contradiction to what we already know about our singular set. So we see that even harmonic functions with single activation boundary values may not actually be in the appropriate function spaces. So this is probably a very initial view at this kind of regularity theory, but what our general takeaways were that for translation invariant linear PDEs, solutions very often lie in barren space. The counterexample is the Laplace equation because the solution has to grow too fast. But if we just add a little bit of pressure, then everything's fine. Boundary conditions, however, break translation invariance, which is what we used in explicit representations. And even harmonic functions with ReLU boundary values are not generally in barren space. So we might need either deeper neural networks, or we might need to look at something else. There are some positive results in this direction by Jianfeng Lu and Yulong Lu for elliptic equations and for Schrödinger eigenvalue problems, but in slightly different barren spaces which are defined spectrally. And nonlinear PDEs may indeed need deeper networks to actually accommodate the nonlinearity, but we can say something if we can, for example, write them as compositions effectively. And that is everything that I wanted to say today. Thank you so much.
Thank you very much for the presentation. We move on to the next speaker, Jie. Are you ready? You can start sharing your slides. All right.
Yeah, can you see?
And we can hear you. Please go ahead.
Okay. Thank you for the invitation. So here I want to present our recent computational work on deep learning methods to solve Fokker-Planck partial differential equations. So this is my collaborative work with Dr. Yao and Matthew Dobson. So we are interested in the invariant distribution of a dynamic system driven by an SDE. It is well known that the density will follow the stationary Fokker-Planck PDE. And the uniqueness of the solution is determined by this integral condition, which is also the resource of difficulty using traditional numerical methods. Okay, so here we use the physics-informed type loss functional in the learning process, where the first part comes from the PDE and the second part is to determine the uniqueness using data, where this data V comes from either the experiments or simply just sampling this SDE to get a multicolor density. Okay, so in this work, we provide some rough analysis of the method. Okay, so if we discretize the differential operator in certain type into a matrix, then we can prove the following limits, which means if the error from data is spatially IID, no matter how strong it is, we can still guarantee the convergence of the method. Okay, so here we, this is the first important observation of in the work. This is a comparison between two learning processes. In the first learning process, we only use data to learn the density function. So if we only use data, we need to use so many data points to get a very good result. But if we add the PDE parts into the loss function, that means we tell the neural network a lot of physics information it should follow. Then we only need to use a few hundreds of reference data to get an even better results, because they are only used to determine the uniqueness, where the location where the function should be. Okay, this is very important because in reality, particularly in high dimensional systems, it is not easy to obtain this kind of data. Okay, because we only choose very few data to learn in the learning process, we need to choose them very carefully. Why? Because, for example, in this example, the invariant measure is highly concentrated in just simply 2 narrow parts, which means if we uniformly sample the collocation points of this data, it is highly possible all of them will be located in the low density parts. But remember, 0 is also a solution of the Vogel-Planck equation. So if we use these low densities, it will be considered as error in the learning process. We will get 0 solution, but that's not what we want. So we provide the following strategy for sampling these collocation points. So first, we just need to run the trajectory of the SDE again, and then choose alpha % data collocations on the trajectory. Then most of them will be located in the high density parts. And then we choose the rest of them using a uniform distribution to represent the information from other parts. Okay. So the other observation is actually the strength of these methods in denoising, and also demonstrates the theorem we proved. To say this, we artificially multiply a random variable to the exact solution of invariant measure, where this random variable follows a uniform distribution, and this parameter alpha controls the strength of the noise. Okay, so you can see this noise is stronger and stronger, and finally it becomes this. So this 0.5 means the noise can be as strong as 1/2 of the true value of the density function. But no matter how strong the noise is, we can still recover a very good approximation of the solution. And in the last row, we show the error both in L2 and L infinity norm, and they are both controlled in a very low level. Okay, so this is all about this work. Thank you all.
Thank you very much, and thanks for staying on time. Next speaker is Johan Rudy. Could you please start sharing?
Yes. And I want to thank the organizers for putting together this conference, and also thank my collaborators, Julie Besack and Amanda Lenzi, who, like also myself, all work at the Argonne National Laboratory, which is near Chicago. So I want to consider an ODE model for spiking neurons. And this is a fairly simple and concise model. The important variables here are the membrane potential, denoted by U, and then gamma and zeta are fixed constants, and the 2 parameters that I'm interested in for creating an inverse problem afterwards are θ0 and θ1. Here's an example output of what these spiking neurons might look like. So blue is the membrane potential. Okay, so while this model is simple from a physiological perspective, in the inverse setting that I will show next, it will exhibit similar challenges. So for solving an inverse problem, it's a good prototype or benchmark model to work on. So, okay, if we formulate an inverse problem, and for the data, we take the membrane potential and add additional correlated noise on it. And if we were to plot the whole manifold of the loss, which we can do for this simple problem, for example, it would have these certain nonlinear features and non-convex features as well. So we see some local minima. We see that the solution would be in this valley, in this narrow valley over here, which shows nonlinear dependencies going around. So obviously, and this is the prior mean, by the way. So obviously, if for this kind of optimization loss, it's very challenging to apply gradient descent methods or Newton's methods, which we would normally do in an inverse problem setting. And this comes really from the ODE, from the nonlinearity of the ODE, and then also that in practice we cannot assume too narrow priors. That means the variance around this prior mean is fairly wide, because there's a lack of knowledge about the parameters in the model. Okay, so this is the inverse problem I would like to solve, and I would like to propose a new approach for it based on deep artificial. So it's artificial neural networks now. Before we had a biological neuron modeled as an ODE. So this deep neural network, of course, has several hidden layers denoted by F sub L. So the L is indexing the layers. And for the input to the neural network shall be the data, which is membrane potential plus noise. And the prediction that the network is supposed to train is the parameters. So theta is a vector containing theta 0 and theta 1. So in the literature, this is sometimes called a pseudo-inverse of the forward operator. So we want the network to directly represent this pseudo-inverse. The hidden layers will be dense, convolutional, or average pooling. And of course, there's some limitations whenever you get to do a method with neural networks, which I just summarized here, but in the interest of time, I skip forward. So the second idea is that we need to generate training data, and for that we use the prior that we would normally take for our Bayesian framework inverse problem. So we have normal priors for the two parameters and also upper and lower bounds for the two parameters. And examples of the testing and training data sets can be seen below. So the blue are the dots are for the testing data, for the testing theta 0, theta 1, and the black dots are for training data. And as you go to the right, the training data increases because we tested different amounts of data and how the network performs. So of course, to generate the full set of training data for each of those points, for each theta 0, theta 1, you need to solve an ODE to generate the corresponding output, which is fed here on the right-hand side. Okay, now going back. So to jump forward to some numerical results, here's a convolutional neural network that performed particularly well. And we've seen it after comparing it to dense neural networks and different
architectures. We have 1 more minute just to give you an update.
Yeah, thanks. And we see the very narrow errors that we get in the prediction. And the paper additionally mentions a bunch of other experiments. Another way of using this neural network is also to predict parameters in the noise, which we also performed. So the neural network was then able to predict at the same time parameters of the ODE and parameters of the noise, which is a completely different model, but it was able to do that as well with careful construction of the data. Okay, and thank you very much.
Thank you very much, Johan. Next speaker is Grant on active learning with importance sampling.
Okay, do you hear me okay?
Yep, but we don't see the slides yet. Oh, here they come. All right.
Okay, so thanks for having me. And in the interest of keeping this in the 5-minute range or so, I've kept this pretty minimal. So I'm going to be talking about a problem that's not unrelated to a few of the other talks that are in this session, which is how to sample in order to solve a particular variational PDE. So let me just start by saying what the PDE of interest is. So the PDE that we're concerned with here is a PDE that defines what is known as the committer function. And so this is a boundary value problem where we specify some domains A and B, and we insist that we have Q equal to 0 in A and 1 in B. And this PDE is relevant for a number of problems in biophysics and chemistry. And it comes from the following type of problem. So imagine that I have a stochastic dynamics, like in overdamped Langevin dynamics. And we know that that's ergodic with respect to a Boltzmann distribution. So I have some, density rho of x, which is equation 3 here. And then with this density, I can define a quantity that's a bit more dynamical, which is known as the committer. And this is the conditional probability that a trajectory initiated at time t at position x in the domain reacts. It's a measure of the time at which it transits to the domain B. So basically in equation 4, you see the definition of the committer, which is just saying that I want to know the conditional probability that if I start at X, I hit B before returning to A. So this quantity is sometimes interchangeable with the notion of a reaction coordinate. It's something that tells me a lot of information about the nature of a reaction. In particular, the isosurfaces of the committer tell me about mechanism and reactive states of a trajectory. So as a kind of minimal example shown in this plot, you see the isosurfaces of the committer as going from white to black for a double well potential. And of course, at the saddle, that's where the transition is. But we are interested in these types of problems for much higher dimensional systems, like things like proteins, as they isomerize or move between two stationary states in a metastable distribution. So there's been some work on this problem, and I just want to highlight precisely what the contributions of our paper actually are. So the first thing that we show is that importance sampling is crucial for this problem. So we really need to use importance sampling, and we can show that this actually improves the generalization error. Secondly, we discuss a strategy for actually doing that importance sampling. And that strategy is one that is active in the sense that it's using an instantaneous representation of the committer to guide the importance sampling. So designing importance sampling strategies in high dimensions is a generically challenging problem, and that's one of the hurdles that we're trying to overcome here. And then finally, we did some numerics to actually show that this algorithm performs well. This is a continuing project. We're continuing to explore this in increasingly complex systems. Okay, so let me show you a little bit more specifically what is actually done. So the PDE that I described before has a variational formulation, which means that we can use gradient-based optimization. So basically what we need to do is sample the objective defined in equation 6 and optimize. The sampling is challenging, however, because the points at which the cost function is actually going to be well resolved are points that are extremely rare under the Boltzmann distribution. The transition interface is at high energy regions, meaning that the statistical weight of the points where the gradient of Q is large are small. So there are few points that you're likely to sample, in the course of just a normal stochastic dynamics where you would actually see the gradient of Q being small or being large. Okay, so there are a few other works, as I said, in this conference talking about this. So let me illustrate, why this sampling is challenging just with a very minimal example. So this minimal example is just a double well potential again, and here we can, sample quite exhaustively. The advantage of this minimal example is that we can parameterize the committer just with a sigmoid function. So there are only 2 parameters to fit here. This doesn't require any, sophisticated neural network machinery. And what you see is that if you do this sampling and look at the empirical loss, it's actually quite different from the population loss, and you miss the solution and you get an empirical minimizer for this problem that is quite different from the exact solution, or the true minimizer. So this is even with quite robust naive sampling. So the interface isn't sampled particularly well, but we have a lot of data here.
About 1 minute.
So, yeah, thank you. So the goal is then to figure out a way of improving the generalization error by sampling better. So we prove a little proposition, which essentially says that for dynamics obtained from an online stochastic gradient descent for the parameters, so those are the thetas, the loss, so the generalization gap, is controlled by a quantity that is explicit. So it's this trace of C star times the Hessian of the minimizer. And C star satisfies an equation which is related to the variance or the covariance of the loss with the gradients of the loss with respect to the parameters. So that's the quantity defined in equation 9. So the goal is simply to minimize that quantity. We do that with a fairly standard importance sampling approach, which is umbrella sampling, but we use these umbrellas in an active way using our instantaneous solution Q as a guide. So we're biasing and reweighting by the committer itself. Okay, and so just to show you that this makes a difference, if we look at the expected solution for an importance sampling scenario with this simple Muller-Brown potential, we get a very good result. Whereas if we look at it without importance sampling, the result deviates. Although the solution looks fairly reasonable, the solution deviates without importance sampling. So if you're interested in this, feel free to talk to me or have a look at the paper. Be happy to chat more.
Thanks a lot, Grant. Next speaker is Hao-Yo Lee. Hi, we can hear you.
Hi.
And we can see your slides. Please go ahead.
Okay. Thanks for having me today. And I will give a talk on our recent work, a semi-group method for high-dimensional commuter functions based on neural network. So the topic is quite closely related to Grant's talk earlier. So this is a joint work with Yuhao Ku, Yinor Ren, and Lexing Ying. Okay. So the commuter function is a central object in the transition path theory. And in transition path theory, we consider systems governed by the Langevin equation, and in this case, the overdamped Langevin equation. And if we define the commuter function as this probability of this system hitting region B before region A, starting from a position X, then this commuter function satisfies this Fokker-Planck equation with a particular boundary condition. So there are clearly two difficulties in solving this equation. One is that the equation is defined on the phase space, which can be of very high dimensions. And we have a particular boundary condition to deal with. In the previous work, we parameterize the commuter function by a neural network and solve this optimization problem where we enforce the boundary conditions through the penalty terms. So clearly we need to evaluate this explicit differentiation in the variational form, and we need to tune the penalty coefficient carefully because the boundary conditions are only enforced through these penalty terms. So that's the motivation for our current work. Intuitively, we want to replace the original equation LQ equals to 0 with the semigroup form I minus e to the delta LQ equals to 0 for some delta. We can rigorously show that the equation can lead to this Qx equals to PQx, where P is defined in this way. It is a semigroup operator, and there's no explicit differentiation in it. Okay. And then we can split this operator into two parts according to whether delta is smaller than tau or greater than tau. If delta is greater than tau, we can just plug in the boundary conditions. And in this way, we can rewrite the original equation with these two parts, Pi and Pb. Notice that we already include the boundary conditions in this equation, even though we we haven't added the penalty functions yet. So with the positive definiteness of PI, we can form the optimization problem similarly with the previous work. Okay, so that's the main part of our method. And so here I will show only one numerical example. We also did the Rugged-Moller example and the Ginsberg-Landau example like in Grant's paper. So the double well potential we consider here is actually a double well along the first direction and just quadratic potential along other directions. So you can see in this figure that numerical solution is a good approximation of the ground truth. In this case, we can obtain the ground truth by variable separation. Okay. And we point out that the final error is not sensitive to the parameter delta in our method. So if you choose different delta, you will obtain basically the same final error. And more importantly, we so on the right side, we compare the current method with the previous method. So you can see that when using different penalty coefficients, the current method behaves basically the same. But for the previous method, the final error and the training time is very sensitive to the penalty coefficient. So we verify that by using our current method, we obtain faster conversions and we reduce the sensitivity to the penalty coefficient. So in conclusion, we show that the commuter function satisfies an integral equation based on the semigroup of the original differential operator. And we remove the explicit gradient in the original formulation. And the boundary conditions are handled naturally with the splitting of the semigroup operator. And we result in a faster and less sensitive algorithm than the previous work. And thanks for your attention. And I'm happy to answer any questions.
Thank you very much for the presentation and for staying on time. So we move now to the Q&A. We already have several questions in the chat. So does anyone of the people want to unmute and ask the question? Sean, please go ahead.
Yeah, I'm happy to. So should we start with a sequential order, starting from Stefan?
Yeah, sure.
Yeah, so Stefan, thanks a lot for your very nice talk and very nice work. I was just wondering, in your analysis, how should I think about the interaction between the activation function, which is something that you're free to choose, and the PDE? So is there like a kind of a optimal activation function that would define the best adapted Baron space?
I don't know. So a lot of what we thought about was for ReLU, because it is nice from the functional space perspective because you've got a lot of freedom in your normalization. And one of the results that I mentioned is definitely very sensitive to that, namely this structure theorem, where we say that the functions, that the singular set has to be straight. That comes from the fact that we've got this non-differentiability. And I assume that other activation functions would have different properties in those spaces. I imagine if we are trying to solve PDEs, that it would not be unnatural to try and look at activation functions which are a bit smoother, but I can't give you anything positive. I would probably mention, I said that there are positive results for how to solve PDEs also on bounded domains by Liu and Liu. And those work in spectral Baron spaces which are insensitive to the choice of activation function. So because they have spectral, the decay of Fourier coefficients is controlled. And so that should work for, I believe, any sigmoidal activation function.
I see. Okay. That's
a lot of open.
Yeah, no, because I was just having in mind this even the simplest example you have with the heat equation, that one would expect that if the activation function is already something that looks a little bit like a Gaussian, it would be much easier, right? To to close basically to have a norm that doesn't even blow up, right? I mean,
yeah.
But I don't know. This is just pure intuition. So anyway, that's yeah, very nice. Thank you.
Okay.
I have a question about the same paper. Actually, it might be a good time to ask it. So we had a really nice discussion the day of the computational mathematics workshop about trying to construct kind of benchmarks and toy problems for these problems of the intersection of numerical analysis and machine learning, right? And one of the kind of success stories that was mentioned was the teacher-student model from statistical physics, where you kind of plant a neural network, and because you planted this network, it gives a simplified setting where you can actually maybe make some claims rather than trying to study, CFAR 10 or something like that. I was wondering, in light of these results where you say, if the initial condition or if the boundary conditions are a neural network, then for some PDEs, the solution is a neural network. Can these results be used to kind of define some benchmark problems for problems of the intersection of PDEs and neural networks, where we know, it's just kind of a lot like a planted teacher-student model, right? Where the solution should be a neural network. So in principle, you can compare the learned solution to the PDE to the, provable existence of a neural network solution.
That makes a lot of sense to me. I think to an extent, though, it is. Those are good spaces to study, from the sense that we know that the solutions can be learned efficiently, and we've got ideas of how many data samples we probably need. I think there are also other classes of PDEs, like parabolic, where we can show that they can be approximated efficiently by very different means, by using stochastic representations. But so I think these barren spaces would probably be good for benchmark problems. The big question, I guess, would be, how realistic is it to have barren data? And if we've got, so are we testing our numerical, we would be testing our numerical methods on the problems where we know they should be successful, but then whether those are the kinds of problems that we are likely to encounter in practice is yet another very important question, I think. So I think it would be one step, but possibly not the end of the story.
I see. Thank you. Very nice talk.
All right, let's move on to the next question in the chat. I think, Grant, you asked the question. Do you want to unmute yourself and ask it?
Yeah, I'll follow up on this. So, in many of these, in many of the problems of interest where you might want to solve a Fokker-Planck equation, you'll have multiple relevant energy minima that correspond to basins in the probability distribution. And I guess my question about this approach is, if you have that sort of metastability, does the algorithm, as described in the talk, actually find the relative statistical weight of those basins without substantial information about dynamical crossings between the basins?
Yeah, this is a very good question. And actually, this is also a difficulty we want to further resolve in the future. So first, actually, Dr. Yao already provide some part of the answer in the chat. So actually, yes, you are right.